Hello students, in today's class let us learn Stokes theorem, that is conversion of a line integral to a surface integral. Okay, now Stokes theorem for a vector field. Now what is Stokes theorem for a vector field? Okay, so let us take a simple closed curve. Let C be a simple closed curve bounding the open surface S. Bounding the open surface S. If U is a vector field defined on S and also on C, then we have this theorem. We have the line integral over the curve C, U dot T ds is equal to the surface integral curl of U dot N ds, where N is the outward normal to ds and T is the tangent vector to the curve C. You can see the diagram here. So we have a simple closed curve. Let us take a simple closed curve. C is the simple closed curve. Okay, no knots, nothing like that, right? Simple closed curve C, bounding the surface S. This is the surface bounded by surface S. If U is any vector defined on both S and C, right, then you have this a very important theorem. You can convert the line integral to surface integral. So look at the integrand. Integrand for the line integral is this U dot T, and the integrand for the surface integral is curl U dot N. Okay, and what is N? N is unit normal of that ds. This is ds. So this is the Stokes theorem for a vector field, and we have studied the proof of this in our earlier UG classes, in our BSc classes. Now let us use this Stokes theorem for a vector field to prove the Stokes theorem for a tensor field. Now same surface, same simple closed curve, we are going to take, instead of a vector field, we are going to take a tensor field. Okay, let us see the Stokes theorem for a tensor field. So Stokes theorem for a tensor field, okay, let us take C. See, as I told you, C is a simple closed, okay, boundary of open surface S. So we have a C closed curve and we have a surface that is S. And if A is any tensor field defined on both S and C, then we have the line integral, okay, over the closed surface, closed curve C, AT ds, the ordinary product AT. A is any tensor field. Okay, we can take order 2. Fine. So any tensor of order 2. So A T ds is equal to surface integral curl A transpose N ds. This is the Stokes theorem for a tensor field. What is our A? A is the tensor field. Okay. Now to prove this, let us take any constant vector defined on S and the closed curve C. Take any constant vector. Our C is any constant vector. And take the dot product of C and the RHS of what we have to prove. So let us consider C dot, the surface integral. Okay, that is the the RHS of this. This is the RHS. Let us take the RHS and take the RHS dot C. Fine. Now since C is constant, we can take this C inside the integrand. Correct? So take C inside Let us call that as equation 1. Equation 1. Now, we have an identity. What is the identity? Very, very important identity. C dot curl A transpose. This is the identity. C dot curl A transpose N is equal to curl A C dot N. We have proved this identity using comma notations in our earlier classes. So, this transpose is becoming without transpose here. So, using this, and also we have curl AC is equal to curl A transpose C. Curl AC is nothing but curl A transpose C. Look at the brackets here. Curl A transpose C. Using these two identities, equation 1, right, will become what? So, same surface integral. So, C dot curl A transpose N is nothing but curl AC, and curl AC is nothing but curl A transpose C. Okay. So, using those two, we get curl A transpose C dot N ds as it is. And let us call that as equation 2. Let us call that as equation 2. So, now what is A? A is second order tensor. A is second order tensor, remember? And what is A transpose? A transpose is also a second order tensor, right? And A transpose into C, the ordinary product, is a vector, and curl of a vector is again a vector. So, it is becoming a vector field. Curl A transpose C is a vector field. So, we have a vector field, we have the surface integral, we have the surface integral of a vector field. This whole thing is a vector now, dot n ds. So, applying what? Stokes theorem for a vector field. Applying Stokes theorem for a vector field, that is equal to, so curl of a vector, no, so vector, right, dot t ds. Dot t ds. So, this is using the Stokes theorem for a vector field. The vector field here is this vector, curl of A transpose C. Okay, let us call that as equation 3. Now, let us use one more identity. What is identity? See, we have this identity. What is identity? A transpose, right, C dot T is equal to C dot A T. We have this identity. We have proved this also in our earlier classes, right? So, using this identity, see, the place of this whole thing, right, that can be replaced by C dot A T ds. What is our C? C is a constant vector, so that can be taken outside. So, dot the line integral A T ds. A T ds. Okay. Now, what is our LHS? So, our LHS is, we have LHS is this whole thing, C dot the surface integral we had, remember, that is equal to, what is our RHS? RHS is this, that is nothing but C dot line integral AT ds. Okay, since C is arbitrary, or C is any constant vector defined on C and S, right? So, therefore, now it should happen for all C. So, therefore, this without C, that is surface integral curl A transpose N ds, must be equal to without C here on the RHS, the line integral C A T ds. And this is nothing but the Stokes theorem for a tensor field. So, any surface integral can be converted into line integral. Okay, guys. So, this completes the theorem of the proof of the theorem, Stokes theorem for a tensor field, using Stokes theorem for a vector. Okay, let us stop now. This completes tensor analysis.